So, good evening everyone. Let's wait for 3 to 4 minutes and after that we will start.
Okay.
So, when is your exam for this course?
It is on 2nd November.
Okay. And have you received like any information like what kind of exam it will be? Fully theoretical or numerical?
Um, no information to that we have received, but I think it would be only numeric objective type, but still it
Like
is
your
not clear,
okay, like your assignment.
like assignment. Yeah.
Okay, okay. I think it's weekday, so other participants are busy in their work.
This time is a regular time for other
No,
examination,
no,
right?
no, no. Actually, no. Actually, last week I was busy. Due to that, I had to reschedule the class.
No, but on
So,
every Tuesday there is again at 6 o'clock there is class by another assistant, Mr. Subrata Mathew.
okay. Okay, okay, okay,
Yeah.
okay, okay, okay. Maybe that's why only you are here. Maybe they are in the other class, or yeah, maybe they are in having some other work because it's quite
No, but
not.
we have
It
received
was
only one link. Only one link, I think so. We have received.
okay, okay. So you have only received one link for today's class.
Yes, yes, only one link.
Okay, what about then the second class?
I think
Nothing.
second class may not be here because in that class, very few people attend that class. Maybe 4, 5 people or 2, 3 people.
Okay, 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 okay. So it's only like an exception. So from like the next week, we will have class on Sunday only, 4 to 6.
Yes.
Okay, so we have waited enough. Now I think we should start now. Okay. So good evening, everyone. I welcome you all to the live session for week 9 for the course Hydrogen Energy Production, Storage, Transportation and Safety. The course instructor is Professor Pratibha Sharma from IIT Bombay, and I'm this course TA Amit Kumar Sharma. So today we are in our live session number 9. So you all know that the purpose of these live classes is to show you the assignments, previous year assignment question, and to give you like a hint you can understand, so that it will be very easy for you to attempt your current assignments, and you can also have a quick revision for the last week. So this meeting is being recorded, and the meeting recording and this PPT will be shared to you from the NPTEL team. So let's start with today's class. So this is the course outline. So as of now, we have covered hydrogen production, and now we are currently in hydrogen storage. Okay, so we have covered like compressed, liquid state, solid state. Now we are in solid state, metal hydride and all. So let's go through the question and the concepts. The question number 1 is select the appropriate correlation as per the Sievert's law applicable to alpha region in PCT. So take 2 minutes. Try to recall the class notes. Let me know the answer. I think we have one more participant. Okay, Mithun. Hi, Mithun.
Yes, sir.
Yeah, is this your first class
No, no, not
or
not.
like you? Okay, 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 okay.
I attended almost all the classes of this.
Answer is
Okay, okay,
answer is
nice.
C.
So then,
Answer is
okay,
C.
so you received the
C.
information for this class.
Yeah, I received. Actually, there was confusion now. On Sunday, there was SMS has come. Okay, there will be class, but in the mail there was information that there will be no class.
Okay, 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 okay.
That was the confusion, I believe. That's why low participants.
Yeah, okay, okay, okay. Okay, no issue. Yeah. So yeah, Mukesh, you were saying something?
As per Sievert's law, the answer is option is C. That the C is proportional to square root of P.
Okay, nice. So what is the Sievert's law? Just basic single line definition. So what is the like meaning of this law? What this indicate? So what we are actually going through, currently we are in the metal hydrides. Okay, and what is the purpose of metal hydride?
To store hydrogen.
Okay,
Basically.
so we are having a gas that is hydrogen, and we are storing that hydrogen in metal hydride. And in this field, we are using this law. So what do you think? So basically, Sievert's law is a rule that predicts how soluble gases are in metals. Okay, so basically, it deals with the solubility of gases in metals. So this relation indicate the CS is proportional to the square root of P. Okay, so your answer is correct. So basically, it deals with the solubility of gases in the metals. Okay, and it is named after German chemist Adolf Sieverts. Basically, here we can see that the solubility of the gas is proportional to the square root of the partial pressure of gas in thermodynamic equilibrium, this P. Okay. So if you go through the class notes, then the the professor have covered the whole derivation of this relation. So for more detail, I advise you to refer to the class notes. Okay. So here is the relation. If you remove the sign of proportionality, then there will be a constant ks. It's a time dependent constant. Okay. So this is the Sievert's law. Now the slope of Van 't Hoff plot is given by A delta h by RT, B delta h by R, C delta s by R, D delta s by RT.
First one delta H by RT.
Delta h
And
by RT. Okay.
this
Okay.
enthalpy
So
change.
let's wait for 2 more minutes. Today we have only 2 participants, so that's
I
why
think
I think yeah.
want of plot is against 1 upon t. So 1 upon t would be in the x-axis. So slope would be delta h upon r.
Yeah, nice observation. So it means that the correct answer will be B, not A, right?
Yes, option B.
Yeah, okay. Let's wait for 1 more minute and after that we will discuss. Okay, so here we can see this relation ln P upon P naught equals to delta H by RT minus delta S by R. Okay, so this is came from this delta G equals to 1 by 2 RT ln P upon P naught. So there is a relation. So if we make a graph between this and 1 by T, okay, so this delta H by R will be the slope, not delta H by RT. Okay, so because you are making a graph relation between 1 by T and ln P upon P naught. So the correct answer will be option B. So this is the Van 't Hoff equation ln P upon P naught delta H by RT minus delta S upon R. So in this the entropy change is constant and 130 joule per mole Kelvin. Okay. So why this entropy change is constant delta S? What is the meaning of this? If you have gone through the class videos, let me know. Okay. So we are considering here hydrogen. Okay. So initially it was in gaseous form, then it is absorbing in the metal hydrides. Okay. So that's why we are considering that entropy in this transition when it react with the metal and generate metal hydride, then in this whole process the entropy change for this hydrogen atom will be constant and that will be value of 130 joule per mole Kelvin. The enthalpy change it depends on the metal and other various parameters. So it is due to mainly the elastic contribution and electronic contribution. Okay. So these are the formulas for elastic contribution, electronic contribution. V22 Ti35 Cr43 can be classified into which type of metal hydride? BCC compound, AB5, AB2, AB.
Is it BCC compound? Because in AB2 there is one single mode. Option A.
Option A. And what is your reasoning?
I can see there are three items V, Ti, and Cr metals.
Okay, okay.
So
Yeah, nice. So the correct answer is option A, BCC compound. Now we will go through some notes and then you will get to know, okay, the answer is A. So it's about the intermetallic hydrides. Okay, so it's Lebowitz et al. In 1958. So it's zirconia nickel hydride. So it's a very totally new field. Okay. So there is then this Midemas rule and all. In 1974, they reported this hydride FeTi and Mg2Ni. These are very popular actually. In 1984, Gleason and Drishan, they give this empirical relation. And also with time, several hundreds of other intermetallic hydrides were reported. So stoichiometric compounds from two metallic components A and B. And the relationship between lattice parameter, unit cell volume, and respective Plato P in different materials. So next upcoming slide, we will see various intermetallic hydrides. So this intermetallic compounds IMC. So it's referred to the intermediate phase between A and B. So allowing two elements increases the degree of freedom in the material formed and leads to various changes. So when we are having two metals together, then it can increase the degree of freedom and it's lead to various changes. So this is A and B. So A, the transition metal or rare earth metal with a strong affinity for hydrogen and thus high thermal stability. So A, we can have Y, La, Ti, zirconia, etc. And B, the transition metal forming unstable hydride, chromium, manganese, Fe, Co, and Ni. So absorbing hydrogen only at high pressure. So these separate two metals, now we will combine them and we will have a intermetallic compound. Okay. So we have AB5, A2B, AB and AB2. So here A is the strong hydride forming element and B is the weak hydride forming element to form intermetallic hydride. So in this we have seen that the A is the rare earth metal with strong affinity to hydrogen and the B is uh, transition metal forming unstable hydride. So AB5, A2B, AB and AB2. Okay. So the different composition leads to different thermodynamic properties. If we are having like you can see if you have AB5, A2B, AB, AB2, so different composition will have different thermodynamic properties. So condition for selecting these hydrides for different applications. So now when you are selecting a compound, okay, a hydride, then you need to also look after the application. In which application you want to use this hydride. So then you need to consider operating conditions, the gravimetric capacity, effect of impurities, its kinetics, plateau pressure, ease of activation and cost and availability. So these are the important parameters that you have to consider when you select intermetallic compounds. So here's we have we can see some example of metal hydride in the form of AB, AB2, A2B, AB5 and all. Okay. So if you see the AB, so here is the example most studied alloy. It's TiFe. Then AB2, then zirconia, manganese, Raman2. So these are the examples. So if you see the BC compound, then we have this V22 Ti35 and Cr43. So the question was about this only. Then saline hydrides, then high entropy alloys. if you see the reversible hydrogen storage capacity, so it's important. So it's changing actually. Okay. So as we have seen in previous slide, that if we change the metals, the composition, then the properties will change. So you can see the reversible hydrogen storage capacity is changing. For ABs, it's 1.5, then 0.9, then 3.3, then 1.28. So it's changing. Okay. Then the desorption also, the temperature of desorption is also changing. Enthalpy is changing. So the properties are changing. The structure, it's having cubic, hexagonal, okay, BCC. So basically we are changing the, so based on our application, you need to, because the temperature is changing, enthalpy changing, the reversible capacity changing. So you need to select the type of metal hydride accordingly as per your application. So that's AB5 type alloy. It's widely studied. So in this we have vast range of compounds, and it's we have ease of substitution in this AB5 type alloys. So where A is lanthanides, calcium, yttria, zirconia, mish metal. So they also have very good electrochemical properties. B is nickel, tin, titanium, aluminium, cobalt, iron, copper. Okay. So in 1969, SmCO5 was studied for magnetic properties, leads to development of AB5 type hydrogen storage alloys. Then the plateau, slope, hysteresis, tolerance to impurities and cycling can be controlled. So with this type of alloys, we can improve these properties. So the most studied one is LaNi5. It have favorable PCT, low hysteresis, and plateau P at RT20 bar, and it can have 1.25 weight% of the gravimetric density. So if we compare this nickel 5, LaNi5, CaNi5, so you can see the weight% 1.46, 1.49, 1.05. Dissolved pressure at 25 is 23 atmosphere, 1.8 and zero point 0.5. See the difference. There's a huge difference. Okay. So we can change this property. So where we are having very high pressure application, maybe we can use this alloy. And if you want to have low pressure application, we can use this alloy. Okay. And between these two, the weight% is not, the difference is not that much, and also the difference is not that much. But if you see the desorption pressure, it's totally different. So for this first one, it's 23 atmosphere, and for this is only 1.8 atmosphere. So if we do the nickel substitution, then we can have this Ni 4.5, Fe 0.85. Okay. So because you can see it's AB5 type. Okay, B is 5. So if you are reducing the nickel, then you have to add something else. So you can see here we have nickel is 4.15, and then we have Fe 0.85 like this. So it's also a kind of AB5. So here also you can compare the weight% and the adsorption and all. Okay. So what are the advantages of AB5 type alloy? So they have good kinetics, good cyclability, low hysteresis, good tolerance to impurities. We also have disadvantages: low hydrogen storage capacity, only 1.2 weight%, and high cost of raw material. Because we have seen that this A type is rare earth metal, so the cost is very high. The capacity we've seen in previous slide is in the range of this only 1.2 weight%. So it's also not good. So these are the disadvantages, but the kinetics are good, good cyclability, low hysteresis, and good tolerance. Now another alloy is AB2. So we have Lewis phase C14 hexagonal, C15 cubic, C36 hexagonal structure. It's the largest group of IMC factors which are important in this is geometry, packing density, valence electron concentration, and electronegativity difference. It is very attractive due to high capacity, good kinetics, long cycle life, but too stable at RT and sensitive to impurities. Structure is Lewis phase alloy. It was first reported in 1960. So in this category, this TiCr2 and ZrCr2 are most studied system. So here A can be Ti, Zr, HF or lanthanides. B is Tm or non-Tm. B is CrM and Fe. So more hydrogen storage capacity than AB5 alloys. So in previous one we were having around 1.2 weight%, but here we can see that it is 1.9 weight% for this TiMn 1.5. Wider temperature range of hydrogen possible. Okay. We can have desired properties, multi-component system uh, we can get in this. So these are some examples of this AB2 type alloys. This TiCr 1.8, ZrMn2, TiMn1.5. So you can see the weight% capacity. Okay, if you see the desorption pressure, so it's see for this ZrMn2 it's only 0.001 atmosphere. Then it's increased to 8.4 for this, and for this it is 182 atmosphere. Then if you have ternary alloys, then it is 1.5 or 2.15%. Okay, these are the pressure. So the meaning of this data is to show you that if we are changing the composition, so the properties are changing. So you need to be very careful when you're selecting the materials for hydrogen storage. So for this AB2 type alloys, we have seen the low hysteresis in TiCr 1.8. The maximum hydrogen capacity, storage capacity is for which is 1.86 or weight% is for TiMn 1.5, and reversible hydrogen capacity is 1.15 weight%. Advantages: higher capacity than AB5, low cost. It also work at room temperature. Disadvantage: difficulty in activation. Then AB type alloys. So these were first studied in 1958 on zirconia and nickel. Showed higher desorption temperature at 300 degrees centigrade. So structure: so ordered BCC. Most studied system is TIFE system in 1970 by Riley and Bisbal. So these type of alloys have absorption desorption at room temperature. Maximum HSC is 1.9 weight%. At HM 0.975, reversible capacity of 1.5 weight%. But also it's difficult to activate these type of alloys. You need high temperature greater than 400 degrees centigrade. In this we have two-step absorption and have two plateaus. These alloys have large hysteresis, and also partial substitution can modify hydrogen absorption. So these are some example. So if you do the partial substitution, it modifies sorption behavior. TIFE, then TIFE Mn. So you can see it's 1.86, and you have partial substituted and modify. So you also added Mn into this. So it's improved 1.86 to 1.9. and the pressure also decreased 4.1 to 2.6. So this difference is not that much, but this difference is significant. So these type of alloy also have good cyclic stability. So the advantage, low good hydrogen storage capacity, low cost operated room temperature. Disadvantages, need of activation step before hydrogenation, very high temperature and pressure required, sensitive to gases impurities and upper plateau instabilities. Then we have solid solution alloys. So in this, dissolving one or more minor element into hydrogen absorbing element or solvent. So we have two minor one or more minor element, and we can dissolve. We can so that we can dissolve these into hydrogen absorbing element. That is called solvent. So unlike IMC, which are stoichiometric or near stoichiometric, this solid solution SS can be non-stoichiometric composition. Okay, it can be formed with PD, TI, zirconia, and B. So PD, low capacity and high cost, zirconia and TI, they are too stable. B, several advantages. The high capacity like TI, FeB, and these. So two plateaus, higher plateau considered 2.58% its capacity and reversible. So it can also, so this kind of composition can also have high cycle life. Many compositional variation of SS alloys, the one with Lew's phase related. So the BC solution is example TIBMN, TIBCR, TIBCRMN. So these are the example of BCC solid solution. So this was first studied in 1980. It's vanadium based BCC alloys most studied. So in these alloys, we can have a maximum hydrogen storage capacity of 3.68%. Okay. So less phase related BCC solid solution are shown better hydrogen storage performance. So the both phases contribute to hydrogenation and have same equilibrium pressure. And this component ZR 0.5 to 0.5 VMN showed three phases: C14, BCC, and oxide. This component have 2% capacity, small hysteresis, and only one activation. So we also have some challenges: destabilization monohydride, or to improve the reversible capacity of dihydride. The advantage of BCC is the operated room temperature and high storage, high hydrogen storage capacity, and disadvantage, difficult in activation because need high temperature, high cost of vanadium, and slope in plateau. Mg based hydrides, so higher gravimetric capacity with lighter elements, so 7.6 weight%, slow kinetics. The desorption is 300 degrees centigrade, ionic hydride, and low cost. It, so we can reduce the size with this kind of hydrides, alloy with other elements, Mg2Ni, MgAl. The composites, so ball mill with graphite carbon mixed with hydrides, MgS2 and TiH2. So in summary, so intermetallic compounds offer a wide variation in the hydrogen sorption properties. We can have intermediate enthalpy of formation. The issue is with the poor gravimetric capacity. And it's possible to use lightweight elements. Okay. So basically we can have a combination of different materials, and we can have a alloy which can use a metal hydride to store the hydrogen based on our application. So you need to select the material accordingly as per your application. The thermodynamics of intermetallic compound cannot be tailored using which of the following method: elemental substitution, doping, mechanical milling, or forging.
Forging.
Okay, let's see. Anybody else?
Mechanical milling.
Okay. So, what is your reasoning with forging?
Actually, we have seen now that elemental substitution is possible, doping is also possible, and mechanical milling is later stage, ball milling and other milling is also there.
Yeah,
So
nice.
I believe it is forging.
Nice. And who is with the mechanical milling? What is your reasoning?
So mechanical milling means just you are grinding the material. You are reducing size. That's all.
So, size is actually a very important factor in this kind of phenomena. No? Size matters.
Okay, okay, right.
So, what happens if you reduce the size? What do you think?
By reducing size, you can achieve more surface area.
Yes. And what do you think? Does surface area affect the hydrogen storage?
Definitely,
Yes.
it increases.
Yeah. So, milling is also important. So, okay. So, the answer is D, forging. Now, we will go through these methods and we will look this. So, what are the challenges with materials? So, the challenges, one is achieving 5 weight% capacity at ambient condition. The challenge to have this much of storage capacity. And the modification of heat of reaction and rate of reaction, and the better understanding of metal hydride bond, then effective way to alter the reaction enthalpy allowing with other elements, so like change of composition, then combine stable hydriding element with unstable hydrides that we have seen in our previous slide, improve rate aid catalyst. Okay, and strategies towards improving the hydrogen storage should be combined for improving thermodynamics and kinetics simultaneously and also achieving high capacity. So these are the challenges we are facing with materials. So we have some methods by which we can address some of the challenges. So the one is elemental substitution. So with this, we can adjust the properties. Okay. So if you see this, so it's MgH2. So the delta H is 75 kilojoule per mole, 400 degree capacity 7.6 weight%. If you have Mg2Ni, then it's changed. Then Mg1 minus X CaXNi. Okay. So you can see the change. So we can see the effect, but it's difficult in modification of the properties by substitution. Correlation between substitution and P equilibrium is so that the composition of the alloy cell volume also. So if you have LaNi5 and you substitute with aluminum, so you will have loss of capacity. Okay. Then TiMn 1.5 substitution on Mn, no loss of capacity. If you replace the Mn, then no loss of capacity, but P equilibrium changes. So it increases for the CuFe and CO. Okay. So this substitution effective in varying equilibrium pressure. So we can do the substitution and we can change the properties. So here in this table, you can see the TIFI, the pressure is TIFE, the pressure 3 megapascal, temperature 313 Kelvin, capacity 0.725, and delta H 13.36. Now it's changed to TI 1.1, FE 0.8, MN 0.2. So this is same, but this is increased. Okay. Now see this one. This is all decreased very near, but this again changed. This is changed. Okay. Similarly for these two, we can change the thermodynamic properties by the elemental substitution. And by doping also we can change the properties. Okay. So this is the alloy TAFE, and if you do the doping of 4 weight% of yttria, then you can see the change in properties. So pressure decreased 3 to 2.5. So the change in capacity, so it increased to 1.8 weight% from 0.725. A huge jump. Then with 4 weight% of zirconia, it's the pressure further decreased 2 megapascal, temperature 298, capacity 1.6. Then in this alloy, this is doping, this is the effect. So doping can have, like, if you do this, then the number of cycle to reach full capacity decreases. The absorption kinetics also affected, and resistance to impure gas or impurities improve with the doping. Now come to mechanical milling. So in mechanical milling, we can prepare new alloys, nanostructures, metastable phases, and the catalyst dispersion. So it can improve the kinetics, okay, of hydrogen reversibility. It can improve the kinetics in Mg hydrides, reversibility in NaAlH4 with Ti doping, and the several plastic deformation occurs, creating nanomaterials, fresh surface, disintegration, dislocation, vacancy, and faults. So if you go for nanosizing, then ball milling, the process, the process of ball milling is the process where the impact of balls and collision leads to nanosizing. So it decreases the particle size, which decrease the diffusion distance between components. It also increases defect density. Then the HPT, in the HPT, the torsional strain achieved by applying high hydrostatic rolling pressure. In rolling is the process where the material is processed by introducing it between rollers where it is compressed and squeezed. These are the rollers. You can fill the material. You can have straight road like this. Okay. So you have also seen this kind of rollers can use to reduce the thickness. So if your plate is like this, so you can reduce thickness like this. But here we are having the in powder form, so we need to do it in vertical way. Okay. So these are the process for ball milling, high pressure torsion, rolling. So here you can see this is the alloy. Then after 0.5 hour milling, so see the change. So the pressure same, temperature same, the capacity changed, and this delta R value changed. Okay. So nanosizing changes physical and chemical properties due to high surface energy. Unsatisfied surface atom bonds and hydrogen adsorption properties can be tailored by nanosizing, but this is complication. Nanosizing improves kinetics, reducing kinetics very different steps of hydrogen absorption. So in summary, we can say there are various ways to tailor the hydrogenation and dehydrogenation properties of hydrogen storage materials. We can do this by elemental substitution, mechanical alloying, nanosizing, destabilization, and metastable phases. So the correct answer for the previous question was forging. Which among the following can be considered as an example of doping? Mg2 NiTiCr 1.1 Mn.9 zirconia Fe2 minus X MnX TiFe plus 4 weight% zirconia.
Answer is B.
Okay,
Option
let's
D.
wait.
It's a TIFE 4 weight% zirconium.
Option D.
D. Option D. D.
Yeah, option D. Okay, we have two answers, option B and option D. Anybody else? Okay, think once again and let me know the answer.
What was the first method before doping?
So we have covered the elemental substitution,
Okay.
alloying, hedging,
Okay. No, I
doping.
think answer is D. Doping. Yeah. Sorry, the answer is D. I think the zirconium before 8%. Yeah.
Doping. Yeah. Okay, so the correct answer is doping, because we have covered in doping means that you have your alloy and just you are adding something extra. You are not changing that alloy directly. Okay, so just you are adding 4 weight% of zirconia directly to it. Okay, that's doping.
So, just have one question. So, this is for week 9, is it, Amit? This.
Yeah, week 9.
Okay. Okay.
Yeah. So actually, this class was scheduled for last Sunday, but I was having some work, so that's why I request to reschedule it. Yeah, that's why we are having it on Tuesday.
Okay.
Yeah. So this week, again, we are having another class on Sunday.
Okay. That is
So
week 10.
week 10. Yeah, in that we will cover week 10.
Okay.
Okay. So the effective thermal conductivity of metal hydride can be increased by using metal foam, surface roughness, heat transfer fluid, phase change material.
So, A. Sir, B.
Metal foam. Yeah.
So we have one answer, metal foam. Anybody else?
Surface roughness, B.
Okay, another answer, B, surface roughness.
It's metal.
Okay, so what is your reasoning behind metal foam?
I don't remember, but yeah, it is explained in the class video lecture by my professor.
Okay, okay, nice, nice. So the correct answer is A, metal foam. So if you remember this equation, the heat transfer Q equals to K delta T by del X. This K is the conductivity. Okay, so to increase the conductivity, we can use metal foams and ENG compacts. Okay, so metal foam, because if you are having metal foam, so like this, so you will have So basically, what is the meaning of conductivity? I think we also discussed in the last class now about with a question. The conductivity we discussed little bit. It's metal and the wooden chair. Remember? Okay. So if you have a metal foam, so basically there will be like complete form of like metal. They will be connected. So if you are having metal we know it's a very good conductor. So automatically the conductivity will increase if you have the metal form, so that it will be easy for the heat transfer, because we need effective heat transfer in our hydride for the absorption and desorption. Okay, so the metal form is the correct answer. Surface roughness, heat transfer fluid, and phase change material. So phase change material, no, because we are looking into the thermal conductivity of metal hydride. So if you use a phase change material, so they have like separate uh, domain, you can say. So not for a particular metal. So and the heat transfer fluid. So it's also not an option for this, because if we are having the metal hydride, so we don't have normally a fluid there actually. We just have the container and the metal hydride in that gas inlet and outlet. Roughness, no. The answer is metal form. So you can see here. So in this way, you can put the metal form. It's the hydrogen inlet. This is the hydride material, and you have with metal form also. So it can increase the thermal conductivity. So ENG compacts and metal form increases. ENG also increase the metal. ENG and metal form increases the effective thermal conductivity of metal hydride and hence result in the faster heat transfer. ENG compacts and metal form occupy volume inside the metal hydride reactor and hence increases the weight and size of the reactor. So if you are adding something extra, so it will also increase the weight. So there must be a trade-off between their effectiveness and dead weight they add to the reactor. Okay, so you need to be aware of this thing. Okay, so there must be a trade-off, because sometimes the weight is a limitation that we cannot have extra weight. So then you should not use the ENG and metal form, but then you will have lower thermal conductivity. The essential condition for hydrogen absorption inside metal hydride is supply pressure greater than equilibrium pressure greater than twice of supply pressure, outlet pressure less than equilibrium pressure greater than supply pressure. I think it was covered in the last week also.
A answer is A.
Yeah, so this was covered in last week also. The supply pressure should be greater than equilibrium pressure. Now calculate the gravimetric storage capacity of an alloy that store 1 kg of hydrogen in 45 kg of alloy. To calculate this, let me know the answer.
Uh, Amit, I just want to have a question. Like H by M, how will you calculate for which alloy is this? I mean, without knowing the alloy.
So the H by M is the hydrogen to metal atom ratio.
Hmm.
Yeah, so the metal atom ratio actually when you are having the composition of the metal hydride, then you calculate the H by M. But
So
here,
here without
no, here you don't have to calculate. So here,
It's
as we have not given, we
2.17%.
have directly given the weight. So you can just consider the whole weight. Suppose if you have not given the weight, then you need to go by this method, no? But you have already given that it store 1 kg of hydrogen.
Yeah, it is 2.17%.
So 1 by 146.
Yes.
1 by not 146 is 46. 45
1 by
plus,
46.
yeah, 1 by
2.17.
46. Yeah. So the answer is 2.17 weight percent. So what is the meaning of this 2.17 weight percent? So what does this 2.17 represent?
That is gravimetric storage capacity.
So it's represent the
Uh,
gravimetric storage capacity. That is the amount
Gravimetric
of hydrogen stored
done
per
in
unit mass. Yeah.
yes. In 45 kg allow can store 1 kg of hydrogen.
Yes. Yes. So if we say 2.1 weight percent, so it is
1
the,
kg of alloy, 2.1% only.
yeah. So is the amount of hydrogen stored per unit mass of the material.
System.
And what is the volumetric hydrogen capacity? Is the amount of hydrogen stored per unit volume. Amount of hydrogen stored per unit volume of the bulk material.
So this amount of hydrogen stored is expressed as percentage or grams or the weight? What is that? Weight
So
percentage?
in this
Gra-
also, the gravimetric is this weight percent.
okay, gravity is weight percent. Okay, okay.
Yeah, it's weight percent. But in volumetric, you can represent in the units of gram per liter.
Gram per liter of the metal. Is it?
Because you are considering the unit volume of the bulk material. It's
Okay. So
volumetric. So you are considering the unit volume of bulk material.
okay. So in that case, the alloy's density can be straight away used, right, to convert to volume.
Yeah, I think
How
so. Yeah.
was
Yeah.
it like? Okay. Because there is a question on this assignment also for week 9, same similar question.
Okay.
So yesterday I was struggling. I didn't understand how to use H by M and all those. And then if I simply divided also, I couldn't get the answer. But I think I'll try again today. Yeah, thanks.
Yeah. Yeah. And if you have any query, so you can email me also. We can discuss.
Yes, so because sometimes we not able to find H by M. The same problem I also getting the same problem. Okay, now
Okay.
we
Okay.
understand. Thanks.
Yeah. So the answer is 2.17 weight percent. Okay. So actually so what is this 2.17 weight percent representing again? Why we are measuring like this? Anybody? Why we are saying weight percent? Have you think about it?
Maybe molecular weight with respect to gas is different. We are
No,
different.
no,
It's
just
basically
no, no, just very simple question. Don't go into that deep
Okay.
actually. Just very
total
think in a very
system weight.
yes,
It is
yes,
a
nice.
total system weight. And with respect to the total system weight, what is the percentage of hydrogen that you can store?
Yes,
Okay.
nice,
Right.
nice.
Right. Right.
Very good explanation. So because when we are dealing with metal hydride, so think in a practical way. How will you suppose if you are having, how will you store the hydrogen and what will be the like the container size and all. So if you want to use in, so then you will have a cylindrical container, and in this you will fill metal hydride, and then you will store the hydrogen in it. Okay, so if I want to measure the how much hydrogen in my container, okay, then this thing is used. Okay, so if your material, you know, the capacity of the gravimetric storage capacity of this material is this much, so then you know you can measure the weight. Okay, this much will be the mass of the hydrogen. So 2.178% means, suppose if this container is now having
Total,
46
total,
kg of,
total, yeah.
yeah,
Total weight,
46 kg of
total
weight.
weight, including the gas of container, is a
Yes,
yeah, with respect to that. Okay.
yeah. So suppose this total container, because hydrogen is inside now, because it's metal hydride, so it's already
Hmm.
reacted. So the total
Correct.
weight you will have 46 kg. But you know, okay, I have used this material, and for this material, the with the experimental data and all, the capacity is around this much. So
Amit,
out of this,
Amit, there are silly questions. Might be I missed some PPT during the live our YouTube session. Why we are storing in this form like hydrogen? Why should not we storage like a petrol, diesel, LPG gas to hydrogen in within the cylinder? Why we going for metal hydride form?
okay,
Just
yeah.
silly question. I don't know why.
No, no, no.
Mm,
Actually, no question is silly.
mm,
Actually, every question is
mm,
important. If you are having any
mm,
doubt, so it's important. So
mm,
the thing is that, so if you, in our initial class, we have compared the density, the
mhm,
volumetric density. That is very
mm,
important. So
mhm.
what is the volumetric what is the density of hydrogen at room temperature?
I forget.
Okay.
That
So
is
the
important.
density,
Okay.
yeah, the density of hydrogen is 0.089 kg
Correct.
per meter cube.
0.089. Yeah. Then.
So this density is very, very low
Mm-hmm.
as compared to other fuels, because you are having your petrol, diesel in liquid form. So they are already in
Ah,
liquid
yes,
form.
yes, yes.
Then
Okay.
their energy value, the energy content will be very high. And at room
Correct.
temperature, hydrogen is in gaseous form, and the density is 0.089. So
Mm-hmm.
it's very, very low. So
Correct.
suppose if, yeah, so if I have a car, then
Mm-hmm.
if I have to run that car for suppose 400 kilometer,
Mm-hmm.
then maybe just for, I'm not exact with the number, just I am giving you an example. Okay,
Mm-hmm. Mm-hmm.
so the suppose I'm assuming that I need like 4 liter of petrol for that car to run
Mm-hmm.
for X distance. Okay,
Mm-hmm.
so you can store 4 liter of petrol in a very small tank.
Mm-hmm.
So
Correct.
that 4 liter of petrol have some calorific value. So basically, you need that much of energy to
Mm-hmm. Mm-hmm.
run your car for X distance. Now to
Correct.
have that exact amount of energy from
Mm-hmm.
hydrogen,
Mm-hmm.
maybe you need to have
More
400
space.
liter 400
Mm.
liter of volume.
My God. Okay. Okay.
Yeah.
Got it. Point.
So
Okay.
it's actually more than 100 times.
Mm.
Okay. So see, so you need so much of volume. And suppose if
Correct.
you also want to store, like I can store hydrogen in liquid form,
Mm-hmm.
then what is the issue? If you want to liquefy the hydrogen, then
Mm-hmm.
you need to go up to 20 Kelvin. Then
Okay.
only you
Temper
can liquefy. Yeah. So it's a
we
cryogenic.
need to cool we need additional system to cool down the
You
hydrogen,
need
right?
to additional system to cool down the hydrogen, but also you need to maintain that system. You need to maintain
Hmm.
your enclosure up to 220 Kelvin only. Then only your hydrogen will be in the liquid form. And if your
Correct.
temperature increases, then again there will be some bubble formation will be there. Then
Hmm.
there will be other phenomena that can
Correct.
hamper the storage. So you
Mm-hmm.
need to maintain the cryogenic storage, and there will be so many issues and all. And also suppose I am having a very small device. Okay, suppose now you are, we can see we are using so many drones everywhere. So I want to use a hydrogen based drone, because
Okay.
now everyone is shifting towards hydrogen.
Correct.
So in future, if you want to use a hydrogen based drone, then it's not possible to use liquid hydrogen, because it's
Correct.
not possible to develop a small device that can store liquefied hydrogen, because
Correct.
we have
Not
to
possible.
invest so much for that, and we only need very less quantity of hydrogen to run that. Then we can use this metal hydride, because we can have a just small cylindrical container. We can fill the hydrogen in that. Okay, we know it will have some weight. So suppose we can store 1 kg of hydrogen in that, in this container, and know, okay, this 1 kg is sufficient for 2 or 3 hours of duration. Then we can easily use, and after we can, when the drone comes back, then you can refill it again.
Okay.
So
Do you mean we are using a satellite and rocket metal hydride, right?
yes, no, in the rockets and satellite, normally they use liquid hydrogen, and
Okay.
also maybe for some components they are also using metal hydrides. But
Mhm.
they are using liquid for sure,
Okay.
because
Okay.
they need, actually, that again the thing is that, see the weight percent. So the thing is that, what is the issue actually na? So
Very,
if you are
very
having,
low. Very,
yeah,
very
very
low.
low, very low. So when you are considering the rocket, then this weight is very important. Okay, so you don't want to carry so much of weight, then
Correct.
you want to store in the liquid form. But if I compare with the submarine, so if you are having a submarine, so their weight is not an issue, their volume is an issue,
Correct.
because when you are underwater, then
Mm-hmm.
the volume is issue, because you know, the volume will have a impact, not the weight
Yes.
that much.
Yes.
So
Yes.
there you
Agree.
can use
Agree.
this metal hydride, because if
Mm-hmm.
you increase the weight, no issue, because if
Mm-hmm.
you have slender and all, then the volume will be very big. You
Correct.
want to have a compact storage, that's why we can use metal hydride.
Mm-hmm.
So it is actually based on the application where you want to use your hydrogen. Okay, that's why we are
Okay.
using the metal hydride.
Okay. Okay. Got it.
Yeah. So nowadays, because this course is from IIT Bombay only, and IIT Bombay is also, the Pratibha ma'am's lab is, they are working on two-wheelers, 2 or 3 wheelers, hydrogen fueled 2 or 3 wheelers. So they are using metal hydride storage, a small cylinder. They have connected that cylinder to a fuel cell. So they are supplying pure hydrogen to the fuel cell, and they are generating the electricity, and they are running the two-wheeler. So see the
Mm-hmm.
application.
So how much liter we can fill hydrogen in two-wheeler and for how much
So
kilometer?
actually it's under development. So I don't
Okay.
have the exact numbers for their experiments, but they are
Because I
doing
also very
this.
curious because you saying the small quantity of hydrogen have a big space of the like to run. That is
Yeah,
the
yeah, yeah. So
yeah.
yeah, so for more detail, you should
Mhm.
go to the previous classes, because in that
Okay.
we have also discussed in detail about the
Mhm.
density, volumetric density, gravimetric density of the hydrogen and all other fuels.
Okay.
Okay, yeah, okay, okay. Let's move further. So the answer is B, 2.17%. Now the rate of desorption in metal hydride reactor can be increased by, option A, increasing the metal hydride bed temperature, option B, decreasing the metal hydride bed temperature, option C, reducing heat transfer coefficient, D, reducing effective thermal conductivity of bed.
By increasing the metal bed temperature because there's an endothermic process. I think so.
Okay, we have one answer.
I think answer is A.
Okay. And what is your reasoning?
Because de-observation process required heat or maybe temperature.
Means we have to remove that hydrogen, so we have to supply some energy.
Mm. Endothermic process actually this is.
Sir, I think it's D, reducing thermal conductivity of bed.
Okay.
Because that equation, Q is equals to K, so delta X is thermal conductivity.
Yes, I think A, increasing the metal bed temperature.
Okay. Reasoning?
Desorption, right? This is.
Yeah. Desorption.
Yeah. So it will.
So what do you
Yeah,
think?
because yeah, the metal hydrate is an forward reaction is exothermic and reverse is endothermic, right? So if you
Yeah.
increase the metal bed temperature, so it will facilitate releasing of hydrogen molecules.
Yes. Nice. So what is the reaction? Well, we have
Uh,
H2.
Plus MHX. MX gives yeah, reversible, and then it is yeah.
So in the forward direction, absorption, it releases heat. For desorption, you require heat. Okay. So if you want to increase the rate of desorption, and what we can do, we can increase the bed temperature so that sufficient heat that is required will be there, and we can have the desorption faster. So option A. Okay. So factors affecting cyclic life of metal hydride: hydrogen supply pressure, thermal conductivity, particle agglomeration, ambient temperature.
Particle agglomeration.
Particle agglomeration. Particle agglomeration.
C.
Yeah, reasoning.
Yeah, I think the hysteresis is because of deformities in the cell structure, the cell structure, lattice structure. So yeah, so that's why I think I can't exactly articulate, but I think yeah, uh, the forward reaction is not always equal to the backward reaction in case of
Yeah, right,
uh,
right. So yes, the correct answer is C, particle agglomeration. So if we consider cyclic life, so in the capacities, kinetics, reversibility, and plateau pressure, etc., all remains constant with the cyclic and during entire life of use. Okay, but the parameters like disproportionation, impurities in gases, particle agglomeration, structural changes, phase changes, formation of non-hydriding phases, they can affect the cycle life of metal hydrides, and these the effect can be improved by the substitution. The correct answer is C, particle agglomeration. And what are the other parameters? So impurities in gases, structural changes, phase changes, formation of non-hydriding phases, and disproportionation. So these are also other parameters that can also affect the cyclic life of metal hydride. Which among the following is the Van 't Hoff equation?
A first.
Okay.
yeah, A. Yeah.
It's a
But I think so. There is minus delta H by RT. I think so. Plus delta S by R.
No, I think A first one is the
A is right, but
Yeah.
first factor is negative, second factor is positive. I think so. No.
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 Actually, A is right. The Van 't Hoff equation is ln P by P naught delta H by RT minus delta S by R. We have covered in our initial slide also.
Yeah, but Amit, I found that at times it's plus delta S by R is also used in the slides in the for the week 9. So I'm just getting confused at times. I mean,
Okay.
say there is an
So
there is a tutorial, right, at the end of week 9. So in that in one of those tutorials for I think problem 2, I saw that plus
okay.
delta S by R is also being used. So
So
it
I
is
have
little
not
ambiguous
gone
in
through the
in check
tutorial,
that.
but
That is
I will
actually
check that.
slope and that is actually slope and intercept when we plot the graph of ln po by p by p0 with respect to temperature. The slope and the intercept is resembling that values which we are saying.
Yeah, yeah. So generally this is the equation that we covered in today's slide also, but maybe it's the sign convention. So maybe they have taken, I have to see the sign convention that they have used in the question actually. Yeah.
Okay.
Somewhere you can find minor delta H by RT also. You can see the previous PPT. Uh, in our last, in this assignment
Hmm.
or maybe in this session, you can find that minor delta H by RT plus delta S by R.
So that I think that will only change the main thing is that the relation actually. So it will be the like the 1 by t and this ln p upon p naught, the slope and the intercept. So if you are changing this sign, then I have to see.
Definitely slope is reverse.
Yeah, yeah.
Sign
So
will change, but
Mm.
the other question I have is what is the value of R we should use is 8.314 joule
8.314.
yeah.
Kelvin, and delta H will be in joule per mole, is it?
So your all the value should be in the sync.
Yeah, yeah.
Yeah, yeah. So if you are using the delta H in kilojoule per mole, so your R value should be also in that. Temperature we need to in Kelvin.
Yeah, temperature always Kelvin, but I think
Yeah,
just that the R values
yeah. So
8.31
R also, yeah, yeah,
joule per mole, right? Joule per mole Kelvin, right? That is
yeah.
the yeah, okay. Because I was trying the assignment problem. I was nowhere near the answer, so just
Okay.
checking. Okay, I'll try again. Maybe. Yeah.
If in case one factor is joule per mole and other factor may be kilojoule per kilo
So
mole, the answer is same.
the just a hint for you. So whenever you are having this confusion, so don't write the values, just only write the units and balance. At the end, you will have the value of this unit. Okay. So just when you are having like numerator and denominator, so your unit should be in balance. That's the main thing. If your delta is taking in kilojoule and you are taking the value of R in joules, then you see this is here only now. So you need to multiply with this 1000 and convert into joule. Then this joule cancel out. So always balance the units. That's the important part. Okay. So first when you're dividing, balance the unit. When you're subtracting, balance the unit. Okay, that's the thing. So whenever you are having any elementary operation like divide, division, subtraction, addition, anything, your unit should be always in balance. Then only you can have the right answer. Okay, so let's come to the next question. The BCC crystal structure have space octahedral sites. 2631.
Six.
Three.
Actually, answer is given in the slide itself. The answer is 3. So if you see here, the FCC have one octahedral site, two tetrahedral, HCP one octahedral, two tetrahedral, BCC three octahedral and six tetrahedral. The value of the hysteresis between absorption and desorption isotherm is given by
Ln
ln
PA by
PA
PD.
Yes. So it's ln PA by PD. So here you can see this absorption, then the desorption. This value is ln PA by PD. So the reversible storage capacity is also of a material is the quantity of hydrogen absorbed and dissolved between the lower and upper operating pressure of a hydrogen storage. There's a definition for reversible hydrogen storage capacity. We have seen in our previous slides this term. So for this hysteresis, this is the answer. For a metal hydride with low delta H value, the required condition to release H2 is given as. Yeah, so in this slide, yeah, it is in minus and this is in plus. So the low dissolution pressure and high temperature, high dissolution pressure and high temperature. Okay. So the thing is that see the difference actually. So in this equation, it's ln P here only. Okay. But if you see the other equation, so if you see that equation,
Yes, so there log PA by
yeah,
P0.
so that's P by P naught. So if you change the orientation of this, then you can have a negative sign and you can transfer that negative sign to this side and your sign will be changed. So it depends on the equation itself. So you need to mention clearly what this P is, then only you will have the correct answer. Okay, so here they
Still,
only mention ln P.
what if P naught is 1?
Yeah, P naught is 1. Okay, so then this they have mentioned maybe the diagram that will
Why am
change
I?
actually. Yeah, the slope will change, the orientation
Yeah.
will change. Yeah.
Okay. So yeah, there's still confusion is there. But okay, if you go to the previous slide which you showed, Amit, I have one question on this
Uh,
delta S. It mentions
yes.
that the delta S is constant for all at 130 joules per mole Kelvin, right?
Yes. Yes.
So we
So
should use
delta.
that value or
Yeah. So
some
delta S is
problem delta is
delta
also.
S. Yeah, delta S is constant. It's given 130 joule per mole Kelvin because we are using the hydrogen. So it's will be in the gaseous state. Then it is absorbing in the metal hydride. So the initial final stage that will be we know the thing and we have calculated, so it will be the constant for all the cases.
So even if the problem mentions some other value, like say 105, 108, we should still take 130, is it?
No problem. If they have mentioned,
Yeah.
then I think you should take that value only. No, if they
Okay.
mention, maybe they are having some uh, so because things are changing, so actually I'm also not aware of that particular problem, but
Okay.
maybe
Yeah, it is
because I'm
assignment.
also, yeah.
I get confused. Like, is it like for the awareness of the students that you should use 130, or I think so that confusion I had. So I'm asking. So yeah, maybe you
Actually,
can
because maybe just I'm not sure I'm right or not,
check.
but
Yeah, you don't have to reply now or answer me now,
yeah,
but
yeah,
just can check later and
yeah,
come back. Yeah.
yeah.
Thanks.
So normally with this equation, it initially given this data, but maybe now new advanced materials are also coming, so I have to check actually. So in this current assignment they have given.
Yeah, week 9 assignment. There's one problem.
Okay, okay, okay. Then
You
I
can
will, yeah, I will look into that. Yeah. Okay, so yeah, for this the answer is B. For a metal hydride with low delta H value, required condition to release hydrogen is given as, so high dissolution pressure and low temperature. Okay.
So this is for favorable lower sub equilibrium pressure, is it? Or so high dissociation pressure and low temperature.
Low temperature. It's for a metal hydride with low delta H value.
Okay. So in this, what are we trying to see? We'll get a delta S as close as possible to zero, or like what is the intent of this?
Okay, so actually I'm also a little bit confused about what is the
What the
intent
question
of
is?
this. Yeah.
Yeah.
Delta H must be low. It means either R is constant, T is high.
So
No, no.
delta H.
Problem is whether for low delta H systems, what should be your pressure, right? That is your ultimate way to absorb or desorb, right? So I was thinking, not getting it. What are we like? Because pressure is the only thing, and pressure and temperature are only thing which is controllable. Other things are internal, right, to the system. So that is very little control we have. So I'm just thinking what is the intent of this question? So yeah.
So if we have high delta H, it means that we have high stability, low pressure, and high temperature for hydrogen release. And if we have low delta H value, then we have opposite. So it means
Okay.
that the pressure will be high and the temperature will be low.
Okay.
So we need to have we required an optimum value for ease of uptake and release of hydrogen.
Okay. So for such systems, for low delta H systems, we need high dissociation pressure and low
And
temperature.
low temperature. And for
Okay.
the high delta H, we have high stability and we need low pressure and high temperature for hydrogen release.
Okay. Okay. Right.
Yeah.
Okay. Okay. Thanks.
So
Yeah. Get it.
basically, the thing is that if you again just come back to the fundamental. So if
Okay.
we want to release the hydrogen, then you need to supply the energy. Okay.
Energy. Yeah.
And
High
what
temperature.
is this?
Yeah.
What is the delta H means? So delta H means that the energy that was released during the absorption and that is required during the desorption is very high.
Correct.
Okay, so if you have high energy, then suppose if system is running, if there is some heat, so very high stability means system is very highly stable, because if there is energy, because suppose your system is still absorbing hydrogen, then it will release heat. Okay, and if your thermal management is not that good, then due to that heat, maybe some part of hydrogen can also release. Okay,
Okay.
we can think in that direction also. So the high delta H means high stability. So we need high temperature for hydrogen release. So we need to have, when we are having desorption, you need to give that much of heat. You need to have high temperature.
High temperature.
But if the
Yes.
value of, the value if delta H is low, then obviously the temperature required will be
Will be
low.
lower. Okay.
Yeah.
Okay. Thanks. Yeah. Thanks.
Okay, let's move further. Calculate the gravimetric storage capacity for an alloy that stores 500 grams of hydrogen in 20 kg of alloy.
Two point four four.
2.44 C.
Okay, we have answer 2.44
C.
C. Okay, so just add the weight of hydrogen and alloy and divide this weight.
Yeah.
Okay, to the hydrogen's weight. So 500 grams. So you need to convert into kg because this is in kg. So total weight will be 20.5 kg and weight of hydrogen 0.5 kg. Now divide both. 0.5 divided by 20.5. You will get the answer. C. Now factors affecting cyclic life of metal hydride.
Disproportion.
Disproportionations.
Yeah, so we have covered in our previous slide, there are multiple factors. So one of these is disproportionation. So the other factors are, yeah, disproportionation, impurities, particles, agglomeration, structural changes, and phase changes. V22 Ti35 Cr43 can be classified as which type of hydride? AB5, AB2, AB or BCC?
C. C. BCC compound.
Yes. So it is BCC compound. Which one of the following is not correct for FeTi alloy? Easy activation, difficult activation, absorption occurs at room temperature. Once activated, well-known traditional alloy.
I think C. I don't know. C must be.
Okay.
Sorry, I missed the previous one. Just I'll go through the question. Yeah. Okay. Okay. Thank you.
Okay.
So, Amit, your slides are slightly different than what the YouTube videos show, right? What Pratibha ma'am shows, right?
No, mostly they
Most
are
of
same.
yeah, but then the previous
Yeah.
slide, I don't remember seeing that yet. Maybe I'm not yet. Yeah.
Okay. Actually, yeah, maybe because maybe in recent class because I'm using the course content of previous years.
Okay.
So maybe they have changed few slides.
Okay.
Yeah. Okay. So for this FeTA alloy, the statement which is not correct is the easy activation process. It's difficult activation process. It's a well known traditional alloys. I think it's from 1970 or 80s. And the absorption occurs at room temperature once activated. The effective thermal conductivity of metal hydride generally lies in the range of
0.1 to 0.3 watt per meter Kelvin.
okay, we have one answer 0.1 to 0.3 watt per meter Kelvin.
No, it's metal, right? So it should be high. I think it's 2 to, should it be 2 to 3? Because iron and all have very high double digit conductivity.
But you have also the hydrogen absorbed in it, na? It can also affect the conductivity.
Yeah, but how much will it bring it down to? 1/10 or 1/100th?
Okay. So the thing is that uh, metal hydride it's not given here like which one is the metal hydride. Generally it is asking. So if you're also using the iron, okay, but it's also depend on the structure because you are having an alloy or that, and what kind of structure is that as compared to the normal iron. Okay, and there are so
Mm.
many structural changes when the hydrogen atoms come into the lattice, then it destroyed the lattice structure and all. So there are so many phenomena. So yeah, it will
Answer
decrease
is
and
C.
yeah,
0.1 to
C.
0.3.
yeah. So it's very low actually. So the answer is 0.1 to 0.3 watt per meter Kelvin.
Yeah. Okay. I started as a guest, but then I was trying to deduce
Yeah,
it from
yeah.
people.
So because the structure is totally changed, na.
Correct,
So
correct.
and also there are so many other things are also going on. So due to that, it decreased so much. Which one of the
No,
following forms a high temperature metal hydride? LaNi5, Mg, FeTi, La.9, Ce.1, Ni5. So it's direct question. So Mg is used to form high temperature metal hydrides. Okay, so now we have still some time left. So we can quickly go through some slides, some more slides about theoretical part of metal hydrides. So this is the basic we have covered.
May I know what is the destabilization process of alloy? Because I want only definition.
What?
Destabilization of the alloy.
Destabilization of the alloy.
Hmm.
So basically that what I'm getting after hearing this term, the thing is that uh, you are having alloy, then alloy is like they are having some conditions for the alloy formation. Okay, if the conditions are different, so maybe the structure of that alloy are not stable.
Mhm. I
Yeah.
gone through Google books, but I not able to find what is destabilization process of the alloy. But that is
So actually,
assignment.
I have to also look into this. So just
Mm,
the thing that that's coming to my mind actually, I just
mm.
so I will go through this and maybe just actually just email me.
Okay.
Yeah, yeah. And I think
I think it's
one of you emailed me a question. I'm sorry for that. If you are present in the class, actually I was quite busy last week, so I was not able to check my mails frequently. So yesterday only I have seen that mail and I will reply to that mail as soon as possible. Yeah. Okay. Yes. Yeah. Were you saying something?
I was saying that I think Mehul here, this destabilization, I think I heard the term in week 8, I think, course content of
Okay.
week 8. Yeah.
Okay.
Yeah. Maybe I don't know if the person who asked this question, if they refresh their
Yeah.
week 8.
So yeah, yeah. Just go to the week 8 course content and maybe you can have more clarity on this. Yeah. So the process is the hydrogen molecules adsorbed on the metal hydride lattice, then they dissociate into atoms, then the atoms occupy lattice site, then diffuse into the metal and form metal hydride phase. So this hydrogen molecule, then they dissolve on the surface, then they dissociate into hydrogen atoms, and then they diffuse into the lattice and form metal hydride. So metal 0.5x H2 MHX plus heat. So in the absorption, so when the supply pressure is higher than the equilibrium pressure, it is exothermic process and the pressure is the temperature dependent. Desorption, when equilibrium pressure is higher than the outlet pressure, it is endothermic process and it release heat and it requires heat. So difference between the equilibrium pressure and supply and outlet pressure is main driving force for the both process. Equilibrium pressure is the temperature dependent and hence heat needed to be removed and supplied during the absorption and desorption process. Now if you are having the absorption, then the heat generated during absorption, it will increase the metal hydride temperature. Okay, then what will happen? The equilibrium pressure will increase. If the temperature increases, the pressure will increase, then the driving force reduces and the reaction stops. This happens. And in desorption, cooling effect during desorption, heat will required. Okay, they decrease the metal hydride temperature. So equilibrium pressure decreases, driving force reduces, reaction stops. So to avoid these things, we need to do removal of heat and supply of heat. So what then happen? What will happen then? In the absorption, the heat generated during absorption increase the metal hydride temperature, then remove the heat. And what will happen? The equilibrium pressure maintained. Okay. So the driving force maintained and the reaction continues. If you don't remove the heat, this thing will happen and reaction will stop. In desorption, cooling effect during desorption decrease the metal hydride temperature. Then you need to supply the heat. When you supply the heat, the pressure will be maintained, driving force maintained, and the reaction continues. So thermal conductivity of metal hydrides are low, 0.1 to 0.3 watt per meter Kelvin, and hence restrict the flow of heat. Okay. This put forward the requirement of efficient heat transfer arrangement for metal hydride. So actually this is a challenge actually to maintain the thermal management of these systems. So this is a diagram of metal hydride reactor. So here hydrogen inlet, then the filter disc type or tube type, then we have expansion volume here, then the metal hydride reactor wall. So pore size of filter need to be lesser than the particle size of metal hydride. Filter is used to separate the metal hydride from the hydrogen during desorption process. Expansion volume is provided to compensate the volume expansion when hydrogen absorbed in metal hydride. Reactor wall must be such that it holds high pressure during absorption and vacuum pressure during desorption. Reactor wall material should not be reactive to hydrogen and metal hydride. And reactor material should be low in cost and light in weight. So some data for volume calculation for metal hydride reactor. Like suppose if you want to store the amount of hydrogen be x gram, the capacity g%, then the amount of metal hydride required will be 100 by g% multiplied by x grams. Density suppose is d kg per meter cube, and the volume metal hydride will be y by d meter cube. Y is the amount of metal hydride in up C. Here they have only mentioned the y by d. Okay, then just don't directly divide this y value by d value. See, it is in gram, it is in kg, so it should be in same units. Then only you will have meter cube. So the porosity of metal hydride powder, it's P, then the expansion volume Z%, then the volume of metal hydride reactor will be 1 plus Z by 100 VMH by P. So these are some formula you can use for the numerical calculation in your assignment. Then when you are having the design of a metal hydride reactor, you need to design something. Then these are the steps you need to consider. First, you need to define the application. So what is your application for the metal hydride reactor? Is it for refrigeration, for heat transformer, for hydrogen transport, for fuel cell, for thermal energy storage, for vehicular, for heat pump? Because each application will have their operating conditions. Okay, maybe there are size constraint, temperature constraint, pressure constraint. So you need to consider all these things and you need to define all the data. Then you need to design the metal hydride reactor. So a clear definition of the application will provide the working temperature and pressure range, and it will also define the amount of hydrogen to be stored. Because if you know the application, then you will know, okay, this is the working temperature and pressure, and this much of amount of hydrogen I need. Okay, based on that, so based on these things, you need to select the metal hydride. Okay, so because you know the pressure, temperature, and the amount, so you need to see the the gravimetric capacity, the temperature, and all things. Select the metal hydride metal, which material you will use for your metal hydride. Then the calculate the volume of metal hydride reactor. You need to calculate the volume. Then find the optimum L by D ratio of the reactor. So L by D, if you change the L by D ratio, so many things changed in the system. So you need to optimize the L by D ratio of the reactor. Then select the metal hydride reactor material. Then find the thickness of reactor according to the ASME pressure vessel code. Then do the heat transfer arrangement. Then optimize the parameters of selected heat transfer arrangement. Then do the performance analysis of reactor. So these are the steps in the metal hydride
L,
reactor
L,
design.
L is a length, D diameter of reactor, right?
Yeah.
Length and dia. Okay.
Yeah. So the parameters affecting metal hydride reactors performance. So the L by D ratio, supply pressure, system cost, external temperature, heat transfer coefficient, system size, and the conductivity. So these are the parameters which are affecting the metal hydride reactor performance. For more detail on each of the parameter, I suggest to refer to the class notes, videos, and a reference book. So use of metal foam and ENG compacts, we have covered this already. It can increase the thermal conductivity of metal hydride. So if you want to increase the heat transfer, then we can have use of fins. So fins are used both internally and externally on metal hydride reactors. These kind of fins of different shapes such as longitudinal and transverse. Fins increases the heat transfer inside the metal hydride reactor and results in faster absorption desorption. Increases the weight of the system, because if you are having extra material, it will increase the weight. Then use of water jacket. Water jackets are used at outer periphery of metal hydride reactor. It provides necessary condition of heat transfer during absorption and desorption, like here the reactor, then the water jacket. So it increases the heat transfer surface area and hence increases the heat transfer. The temperature of water inside water jacket is another important parameter, because the temperature is very important. We need heat and it will release heat for the absorption desorption. So you need to maintain it. Heat transfer is the core problem in this case. Then the cooling tube. So the cooling tube increases the heat transfer surface area and hence heat transfer inside the metal hydride reactor increases. We can have uniform heating and cooling possible. Helical tube, U-shaped tube, straight tubes are some of the commonly used cooling tubes. It's occupy volume inside metal hydride reactor and hence increases the size of reactor. Because you can see in this reactor, these are the tubes. So if you're using 4 tubes, multiple tubes, these are the arrangement of different tubes, okay, to have the proper heat management. So will increase the volume, they will occupy the volume. So if you want to have a fixed volume of reactor, then you need to increase the size. Increment in the heat transfer coefficient. So this can be done by increasing the velocity of HTF. Then the type of HTF is also important to maintain heat transfer coefficient. The cooling tubes, water jacket, and hydrogen inlet. And the combination of methods. So here we can have fins, cooling tubes, water jacket. Okay. So the cooling tubes along with fins are also used along with a metal foam. Inside the metal, we are also having metal foam in the reactor. The absorption and desorption are faster in these cases due to faster cooling and heating. The cooling tubes of various combination along with fins of different shapes are used. So normally when you want to have your own reactor, then for the optimization, first we model the reactor in a software like COMSOL or ANSYS. Then we will do these kind of testing on the model itself. Okay, what is the this management and all. Then only you will decide, okay, this design is the perfect. Then you will fabricate, and then you can compare different designs. Like once, suppose you are having 10 designs initially, then you find, okay, these 2 or 3 designs are having similar result. Then you can do the experiment and check, okay, which one is the good one, and you can optimize that. So this is the way. So basically you can have combination of methods. So you can do all this in the simulation. Then the application of metal hydride reactors. So if the refrigeration, then the storage and the integration. So if you are using it for refrigeration, then your focus should be on the desorption. So the temperature of metal hydride reduced, the extract heat from the space to be cooled, and cooling effect produced. So because if we want to do the refrigeration, we want to have cooling effect, then your focus should be on desorption. Then thermal energy storage. So energy storage is possible at very high temperature, 700 to 800 degrees centigrade. The energy storage have high energy density, long-term storage is possible, heat losses are very less. The space requirement is less compared to other energy storage system. And fuel cell integration, like I told you, they are developing a two-wheeler in which they're using a metal hydride, a fuel cell, and producing electricity, and using a automobile to use this electricity as a power source. The metal hydride reactor connected to the fuel cell is an auxiliary way to generate electricity. The output of the fuel cell is water vapor, which is eco-friendly, and synchronization of hydrogen flow rate need to be considered. Okay, guys. So
one question I have, Mehul here,
yeah,
Amit. So
yeah,
on the
yeah, Mehul.
refrigeration, what is the temperatures we're looking for cooling? What range of cooling temperatures?
So cooling effect produced. So actually, if you are having refrigeration, then obvious, I think it will be very low temperature. So maybe
Like
different kind of, yeah, yeah. So then maybe the material that you will select for the desorption absorption for
Mhm.
the metal hydride reactor, then the desorption should happen at a very low temperature. Then only you will have this cooling effect.
Okay. So, but then it's like -10, -20 degrees Celsius.
Or
What kind of
the other thing is that actually you need actually maybe that is not the case, because the thing is that you need to extract heat. Okay,
Mm, mm,
so the temperature should be lower than that actually. Then only it will extract.
extract the heat? Is
Yeah,
it okay? But do you
yeah,
have
yeah.
do you have practical?
So I don't
Uh,
have any idea about the example of which material. Yeah. So you need to Google it.
okay, I'll try then.
Yeah.
And for this absorption for storage during storage, okay, that is a different thing, right? Because that's an exothermic, so heat is released.
Yeah.
What temperature ranges is the heat released? 200, 300 degrees Celsius. What is the range? Any
So
idea?
in this one,
Yeah, that one. Yeah, first one.
so
Yeah.
in this thermal energy storage, we can see here like, okay, so you are having this thermal load, okay.
Like when you say it is exothermic, what is the temperature rise do we normally expect from metal hydride?
Okay, okay. You mean to ask that? Okay, okay.
Because
So
in the previous reactors, when you were trying to show the reactor part, I just want to get a
mhm,
feel of temperature in the numbers actually.
yeah, yeah. So
Like say
actually,
for 1 kg of metal hydride, the temperature rise is about say 300 or whatever the number be.
so yeah, yeah. I remember. I don't know the composition of the material, but I
Okay,
have
but I
gone
don't,
through.
yeah,
Yeah,
this is
I've
about
gone. I've gone through a material that can really that can the temperature increase in the range of 90 to 100 degrees centigrade.
In that range, okay. Okay.
Yeah, for that particular material. So it will vary depending on the material to material. But for that
Okay.
material, it was 90 to 100.
And what is the mass roughly? 1 kg, 2 kgs?
So no, that was in I think grams actually. So that was a very small reactor. So that reactor was only storing around 70 gram of hydrogen. Yeah.
Okay. Okay. Right. Thanks.
So you can find in any textbook. Yeah. So it depend on the material to material actually. Yeah.
Okay.
Okay. So anything else? So for further, if you have any further queries, you can email me. And I think one of you have already emailed me a query. So I was not available last week, so I was not able to respond. But I will respond very soon. And the next class will be on Sunday only. Okay.
Okay. Thank you.
Okay, thank you.
Okay, guys. Thank you.
Okay,
Thank you so
thank you,
much.
thank you.
Thank you.